Okay, so what is a GLM? I'm going to introduce the GLM conceptually. So in lectures 4 and 5, we put forward the linear regression model as a means of representing a linear and parameters relationship between a continuous dependent variable and a set of independent variables. And for inference and testing, we further assumed that the dependent variable was normally distributed with mean mu I and variance sigma squared. So in lecture 6, we showed that data transformations can help meet the assumptions of a linear model, for example, to invoke normality or to break functional dependence between the variance of y and the mean of y. That is to say, to stabilize the variance. But throughout all of this, we kept the normality assumption in place for inference. Now in this lecture, we're going to abandon that assumption. An alternative and often preferable approach is to model the data on its original non-normal scale of the response and to retain the mean variance relationship rather than trying to remove it. And to achieve this, we're going to introduce the generalized linear model, which provides an elegant unifying framework for modeling non-normal continuous and discrete data with non-homogeneous variance. So I'm going to introduce or try and demonstrate the concept of a GLM using two examples that we'll use throughout the lecture. The first is taking data from the Titanic. The Titanic, as you know hopefully, was a passenger ship that sank in April 1912 after colliding with an iceberg. And the data that we have available record information for a sample of just over 1,300 passengers, and for each passenger we know their survival outcome. Did they survive or did they not? So this is binary, along with their class of travel, their age, their sex, their fare, and some basic information on their family relationships. So we want to model survival outcome as the dependent variable, for example, to ask which characteristics were associated with a higher rate of survival. Now the plot shows the dependent variable. This is our the dependent variable, the response that we want to model. And as you can see, it's binary. It takes the value of 0 if the passenger did not survive, and it takes the value of 1 if the passenger did survive. So of the passengers in the sample, 500, or about 38%, survived, and 809, or 62%, did not survive. But from lecture 1, what we know when we looked at probability distributions is that the relevant distribution for this binary random variable is Bernoulli, with the probability mass function looks something like the one shown on the slide. This is not a continuous random variable, and clearly we can't assume that y is normally distributed. The assumption that the binary variable survived or did not survive is normally distributed clearly will not hold. So that's data that we would not want to assume are normally distributed. Instead, we want to assume this distribution shown in the slide. The second example I'm going to use throughout the lecture is based on collision data from a motorway in just outside London, surrounds London actually, called the M25, the large orbital motorway around London. And these data record road traffic collisions, or what we're going to call RTCs for short, on the M25 and surrounding links, 266 links in total, along with information on traffic characteristics. And we want to model RTC count per link as the dependent variable. So if that tells us for each link the number of collisions recorded within a fixed interval of time and space. Now the plot of the dependent variable illustrates that this random variable is discrete and it has an integer nature. It's a count, so it takes non-negative integer values. That is, it tells us the number of events in a fixed interval of time and space. And from lecture 1, we know that the relevant distribution for a count-based integer is a Poisson-based distribution with the mass function shown here. And again, this is not continuous data. It's strictly non-negative. It is count-based. It's an integer. So the assumption that this data should be normally distributed will simply not hold. It's not a normally distributed. We can't make this assumption here for this type of data. It's inappropriate. So here's the concept then. The concept of a generalized linear model, the objective is to model variation in the mean of a potentially non-normal response distribution in relation to a set of explanatory variables. So we're going to allow the response to be non-normal. We'll continue to do this in the same way in principle as for a linear model, that is via a conditional mean response regression function. So the expectation of y given x is equal to the mu of x beta. But the Gaussian linear model, as I've just said in the two examples, is not applicable when the data are not distributed normally. Why does this matter beyond inference? We'll take the two examples we've looked at. A linear model for road traffic collisions would potentially produce negative and non-integer predictions, and collision counts cannot be negative and they can't be fractional. Similarly, a linear model for the Titanic survival based on a normal distribution might produce probabilities of survival that are less than 0 or greater than 1, probabilities that make no sense under the laws of probability because the normal distribution would not constrain the probabilities to take the values that we need. And we're not going to be able to get around this problem by applying a transformation as we did in the previous lecture. Instead, we're going to use generalized linear models, GLMs, and these are going to allow us to model the data following actually a wide range of distributions, respecting the constraints of those distributions. So counts are going to be modeled as counts, as integer values, and probabilities in the binary case are going to be bounded between 0 and 1. And the GLM is going to do this with estimation and inference based on likelihood theory. One last point, the families of distribution that a GLM can handle include the normal distribution itself. So the linear regression model can actually be formulated as a specific GLM in which the response is Gaussian, and we'll look at that throughout the lecture, and that will enable us to link what we learn in this lecture to what we already know about